as said, I'll present the numerical method at the beginning, and this is this has already been published on the European Physical Journal Plus, and there you will find all the details of the numerical algorithm and the validation and the calculations. So, okay, I'll just go quickly through an introductory part. So, as we all know, superfluid helium can be described as an intimate mixture of two fluid components, so a superfluid component and a normal fluid component. So the superfluid component is related to the phenomenon of Bose-Einstein condensation, even if it's not entirely correct to relate the condensate part to the superfluid part to the condensate fraction. It has the superfluid has its own density field ρs and its own velocity, which we indicate with ds, and he's the closest real example of fluid which is closer to the Euler fluid, as it is an implicit fluid which doesn't carry any entropy. On the other hand, the normal fluid is a gas of elementary excitation, thermal excitation, which are called phonons and protons, and in the temperature range we are interested in, the normal fluid density is mainly due to protons. And so also in this, also the normal fluid component has its own thermodynamic and kinematic variables, so density and velocity, which will indicate respectively with ρn and dn. Given the mean free path of the protons at the temperature in the temperature range we are interested in, the normal component can actually be considered and described as a fluid, and a fluid which has a non-vanishing viscosity and entropy. So it is it can be considered at all effects like an ordinary classical viscous Navier-Stokes fluid. So importantly, in helium 2, when the velocity difference between the two fluid components is larger than a certain threshold, so some critical velocities, then we some quantized vortices nucleate in the superfluid components, and these vortices are topological defects of the superfluid component and are effectively one-dimensional structures. Importantly, the superfluid velocity field is confined to those vortex lines, which are actually, so the vorticity field is actually a delta supported distribution. Around these vortex lines, the circulation of the velocity field is quantized in terms of the quantum of circulation, which is given by the ratio of the Planck constant to the mass of the helium atom. As a result, the superfluid velocity is given by can be expressed as a sum of any potential flow depending on the macroscopic boundary conditions, which here is indicated in blue, and wanted to have a pointer, but it doesn't work. Okay, and also the velocity field generated by the singular vortex distribution, which is obtained via the Biot-Savart law, which you find here in red. Very importantly is that these vortex lines are actually scattering center for thermal excitation, meaning that the interaction between the protons and the superfluid vortex lines gives rise to an exchange of momentum. So at all effects, we can consider the existence of vortex lines, so the existence of regions where the superfluid velocity is different from zero, leads to the existence of the mutual friction force between the normal fluid and the superfluid component. We shall indicate this mutual friction force with F and S. So in the years, there have been many different models of this mutual friction force. The first pioneering work was performed by Hollenbein in 1956, and since then, there have been almost 3 different approaches to model this mutual friction force, and this depended on various factors. So, which length scales of the flow the researchers were interested on, what type of configuration of the vortex fluid tangle, if, for example, ordered in a lattice or a random configuration was investigated, the physical effect of interest, and not completely unrelated to the numerical summations that researchers intended to perform. We shall subdivide these models of the mutual friction force in three in three categories. So there is the coarse-grained framework, which is the framework elaborated by Hall and Bynum, which describes the mutual friction force at macro scales delta, much larger than the average intervortex spacing L. Then there is a local kinematic model, which it models the friction at scales delta smaller than the average intervortex spacing, and in this case we have an imposed normal fluid velocity field, as we will see in a moment, and then a fully coupled local approach, which is at the same time mesoscopic in the sense that the length scales investigated are smaller than the average intervortex spacing, but at the same time the normal fluid is evolved self-consistently on the with respect to the motion of the superfluid vortex lines. Okay, so the pioneering work by Hollenbeinen in 1956, which was composed of two papers which were published back to back, one experimental and one theoretical, describes and elaborates a model for the mutual friction force at scales delta, which are much larger than the average intervortex spacing. This means, as you can see here here on the right, that representative volume element of the fluid is threaded by many vortex lines. On this scale, the superfluid and on this coarse-grained scale, the superfluid velocity and vorticity are actually continuous fields. So we lose the discrete and singular nature of the quantized vortices, and so the superfluid velocity and the superfluid vorticity are averaged on this length scale, and these are smoothly varying with respect to the position. And in this, because the intention of Hollenbeinen was to model an experiment with the rotating helium bucket. In this approach, the vortex lines are considered to be locally aligned. So we have a perfect polarization of the vortex tangle. This approach combines both quantum mechanics, for instance, in the calculation of the scattering the scattering length, which a roton sees while it is scattered by a vortex line, and also a classical fluid dynamic approach, for example, by when determining the Magnus force that the superfluid vortex undergoes because it is immersed in a ideal fluid with non-vanishing circulation. The expression which was derived for the mutual friction force in this coarse-grained model was an expression composed by two different parts. In both terms, you can see the presence of the superfluid vorticity, of the average superfluid vorticity, and there are here two temperature dependent friction coefficients, so which is B and B prime, and interestingly and very importantly, with this derivation and the expression determined matched very well with the experiment, and so the friction coefficients B and B prime, dependent on temperature, were determined by fitting the experimental data. This coarse-grained approach was then generalized by Bekarevic and Kalatnikov, and so leading to the formulation of the whole Bekarevic-Kalatnikov equations, also named HVBK, which have allowed in the decades since 1956 to achieve some very important results, both analytically and numerically. Then, after 20 years later, there was another approach, which was implemented by Klaus Schwarz, and it is an approach which then gave birth to the so-called vortex filament method. It is actually can be considered actually as a downscaling of the coarse-grained model by Hollenbeiner. And here the relevant length scales that are of the flow which are investigated are the length scales delta, which is used to discretize the vortex filament in a number of vortex points. So there are important assumptions behind this vortex filament method. So actually, by downscaling the approach by Hollenbein, this model actually neglects the back reaction of the vortices on the normal fluid. In fact, in this case, the coefficients which Klaus Schwarz determined were only a redefinition of the friction coefficients B and B prime that were derived by Hollenbein. And therefore, actually, in this case, the mutual, the normal fluid evolution is entirely decoupled from the motion of the vortex filament, and therefore it is completely determined by the macroscopic boundary conditions of the flow. Therefore, in this case, in order to make this simulation and to make advance in the field, the normal fluid must be prescribed depending on the fluid dynamic characteristics of the system that we are interested in. In addition, the fact that Klaus Schwarz used the framework of Hollenbein at a scale delta smaller than the average intervortex spacing L, and it used this approach in modeling any arbitrary vortex tangle configuration, as the one that you can see here on the right, means that he assumed that the force which was felt by a vortex line element for example, in a random tangle was the same as the mutual friction force which was experienced by a vortex line element in a perfectly straight, in a lattice of straight vortices. So with this assumption, Klaus Schwarz derived this expression for the mutual friction force, where you can see that the alpha and alpha prime, the friction coefficients, are just, as said already, a redefinition of the mutual friction coefficients determined by Hollenbein. In this case, the normal fluid velocity Vn is imposed, and it depends on the actual system that we are investigating, and it is calculated on the filaments so as it is Vs. And in this case, of course, there is a calculation of the Biot-Savart interval, which in these earlier works by Schwarz was simplified with approximated with the local induction approximation. This mutual friction force then combined with the Magnus force felt by the vortices allowed Klaus Schwarz to determine an equation of motion of the N, and in this case, NP vortex line elements in which the vortex line has been subdivided. So here you see that from this equation of motion of this Lagrangian model that there are the two friction coefficients appear in this equation, and actually in the values of alpha prime are one order of magnitude smaller than alpha. So actually it is the second term which determines the dissipative dynamics due to the mutual friction force. So this local kinematic model, as said, it didn't take into account the back reaction of the superfluid vortices on the normal fluid, on the normal fluid, and therefore depending on the system we wanted, or researchers wanted to investigate, the normal fluid velocity field had to be prescribed a priori. So, for example, in numerical simulation performed using this local kinematic model, different types of normal fluid velocity were used. For example, a uniform flow was used to simulate the counterflow, the Helium II thermal counterflow in the case, for example, far away from the boundaries. Then we have that parabolic Posoi or Hagen-Posoi or Tay-flattened flows were used to investigate the flow, the counterflows or the co-flows of helium-2 in plane channels or in channels of square cross-section. Then vortex tubes or ABC flow for the normal fluid were used to understand what was the response of the superfluid vortex tangle when the normal fluid had concentrated vorticity. And at the end, to try to understand what effect could the turbulent normal fluid flow impose on the vortex tangle evolution. Some random synthetic turbulence with random waves was used, or also some frozen time snapshots of turbulent solution of the Navier-Stokes equation were used. So in this framework, we imposed the normal fluid, and then we studied the evolution of the superfluid vortex tangle. Since then, however, to have a bigger picture of and a more complete picture of what was going on, so the community has started asking what happened if we consider the back reaction of the superfluid bodies on the normal fluid flow, and so if we made simulations which are fully coupled. So both the normal fluid influenced the vortex tangle as in the kinematic model, but also the motion of the superfluid vortices with respect to the normal fluid had an impact on the normal fluid itself. There are this approach could, for example, shed light on different aspects, which nowadays, which with the kinematic model, where it was not possible to do. For example, it could one of the interesting features to look at was what structures in the normal fluid are created by the forcing by the vortex lines, or also looking if the vorticity and helicity locking, which is observed with the kinematic model, if this still holds in a fully coupled model, and also to investigate the energy transfer via the mutual friction which occurs between the two fluid phases. At the same time, also the fully coupled local model is also needed in order to, for example, to interpret and to model experimental results. So, for example, also there are experiments where the turbulence is created by injection of vortex ring, and then at a certain point in the ring injection is switched off, and we see the decay. In a fully coupled model, it would be possible both to see the onset of turbulence and then the decay. Also, the experiments now recently with PTV showing some particularities of the fluctuation of the normal fluid velocity, which is ascribed to the wake of the created by the superfluid vortices moving with relatively to normal fluid, could be, for example, investigated with a fully coupled model. Then finally, also a fully coupled model would allow to investigate also the intermittency problem, as it has been suggested in a recent paper that in quantum turbulence the intermittency is enhanced with respect to classical turbulence, and this enhancement is larger where the mutual friction force is stronger. So in this, because this fully coupled model was started, to be investigated in the early 2000s, and by work by Demos Kivotidis, Carlo, and collaborators. And so because there is a mismatch actually between the average normal fluid velocity on length scales larger than the average intervortex spacing and the actual normal velocity fields, which is perturbed by the moving vortices, the first issue that has to be faced was a redetermination of the friction coefficients. And in this case, the friction coefficients were expressed in terms of the friction coefficients elaborated by Klaus Schwarz, which goes back to the Hollenbein formulation, the rotor mean free path lambda, and the penetration depth beta. This approach was used initially only for simple configurations. For example, here on the right, you see the so-called triple vortex ring structure. So you have the moving superfluid vortex ring in initially quiescent normal fluid creates two normal fluid rings. The blue one, which is the big one, which is in front of the of the superfluid vortex ring, and the red one, which is slightly behind. And then also it was used to understand what is the structure in the normal fluid created by a moving superfluid vortex line. Here the vortex line is perpendicular in this picture on the bottom right, is perpendicular to the plane, and it's moving in the rightwards direction. You see that there are two dipoles are created. This framework elaborated by Carlo and his group in the early 2000s was extensively used by Kyvotides to understand the coupling between the normal fluid and the superfluid. However, the range of scale which was reached and was not very huge, and also the turbulence in the normal fluid and in the superfluid could not be attained in a statistical steady state. So this was the state of the art till a couple of years ago, when always Kyvotides formulated an alternative model to the fully coupled model described in the last slide. And it is a model based on classical low-Reynolds fluid dynamics. And so this approach stems from the following facts. So first, if we look at the Reynolds number of the normal free flow past superfluid vortex ring, the Reynolds number is very small, especially due to the fact that the vortex core is very small. Then, if we look at the dissipative term of the hollow environment formulation, it actually behaves very similarly to the drag force exerted on the moving fluid by a classical viscous flow. And in addition to the flow locally, the vortex seems like a cylinder. So this led Kyvotides to elaborate a framework where actually each discretized line element of the vortex line behaved like a cylinder of a finite length and radius. In our model we start exactly from here, but by noting that it is quite rather unphysical to take into account the length of the vortex line element, so the discretization on the lines, because in fact it is several orders of magnitude the size of the vortex core. And so we used an alternative formulation, always within the classical low-Reynolds number fluid dynamics, and we found that, and we derived this expression for the mutual friction force, where we see that there is a coefficient D which depends mostly on the normal fluid density, the viscosity, and the Reynolds number here at the denominator. With this expression of the mutual friction force and the Jordansky force and the Magnus force, we were able to derive the equation of motion of the single vortex line elements. And you see that compared to the previous expression by Schwarz, the equation is very similar. So instead of alpha and alpha prime, we have beta and beta prime. In this case, the friction coefficient beta and beta prime only depend on these three non-dimensional parameters. So the ratio of the density, which is function of the temperature, the ratio between the quantum of circulation and the normal fluid viscosity, which is also only function of temperature, and then the Reynolds number. So this is, for example, on the right is what we get with our simulation. I will come back to this later. Interestingly, if we compare the dependence of the dependence on the temperature of the friction coefficients most responsible for dissipation, so beta in our case and alpha in the case of Schwarz, we see that we have a very different behavior. So that with the increasing temperature, our coefficients beta decrease, while we know that alpha increases with temperature. I will also come back to this apparent paradox, showing that there is no paradox at all later on. So in our fully coupled approach, as in the coupled approach that were elaborated since early 2000, the normal fluid velocity is not imposed. It is, but is computed self-consistently with a slightly modified Navier-Stokes equation, where the modification is to take into account the value of the mutual friction FNS, which is here indicated in red. So you see here that now there is rather an issue which might seem technical or rather numerical, but actually it has a big physical impact, and it is important. It is very important in the modeling. So here you see that in the grid cell, you have in blue you have the vortex points, and in green, with the green arrow, this is we have indicated the mutual friction force that line element centered in SI exerts on the normal fluid. This force has to be distributed on the normal on the neighboring grid points of the normal fluid grid, where we compute the normal fluid velocity, and this has to be done by using some weights, some appropriate weights, which we have indicated with W, and then by multiplying W by the force, then we redistribute the force. Of course, because the scheme has to be conservative, so the sum of the weights has to be equal to 1. So there are different ways, arbitrary ways to extrapolate this force on the neighboring grid points. So, for example, we can use nearest neighbors, or we can use a linear extrapolation. But then once we extrapolated the force on neighboring grid points, then we might apply some filtering. So, for example, a moving average with n filtered points, or a Gaussian kernel with of width given by a number of an integer number times the grid spacing. The question is whether the results depend on the filtering and on the extrapolation method. So what we did is that we took a single vortex ring in initial quiescent normal fluid, and we observed its shrinking dynamics, and the vortex ring, of course, shrinks because of the friction with the normal fluid. And we see that, for example, in this case, we used as extrapolation method, we used the nearest neighbors, and then we apply the filter, and we see that the ring, the evolution, the temporal evolution of the ring with respect to time, we see that it strongly depends on the type of filtering adopted. So in this case, it is rather clear that these differences are spurious. They are not physical. They depend only on numerical procedure. So we looked for physically consistent regularization. So the problem which we are facing is actually very similar to the what researchers in classical turbulence face when they have to treat active matter systems, where there is like there are point particles, like, for example, particle used in PIV or PTV experiments or bacterial swimmers, when these point-like particles retract on the classical turbulent flow. And so this problem was tackled and solved in classical turbulence by a group by Casciola's group in University of Roma La Sapienza, and it is based on the following assumptions. So, as we have seen, the Reynolds number is very small, and actually the main physical phenomenon on which it is based is the fact that the localized vorticity generated by the moving vortices is then diffused by viscosity, and in a natural way, so without introducing any arbitrary numerical technique. So actually, accordingly, following the classical approach, the approach developed in classical turbulence, we introduce a time delay epsilon r, which is the time delay which which is the time during which the vorticity created by the moving superfluid vortex, the time it takes to diffuse to the smallest physical relevant length scale, so the grid spacing. And in this case, we use the fundamental solution of the diffusion equation to regularize the solution. And so the force, the delta force, the mutual friction force, which is delta shaped on the superfluid vortices. And so we have that the friction, which is originally delta force, gets regularized by this Gaussian, which is this fundamental solution of the diffusion equation, and by the means of this time delay. And so we get that Navier-Stokes equation, which has included a friction force, which is computed with this time delay and which gets regularized by the Gaussian function. So just the last word about the model before going to results. We also we also developed a new numerical architecture, which actually is separates the process of integrating the Navier-Stokes equation and the evolution of the vortex angle into different cluster nodes. And this allows us to reach very high numerical resolution, so up to 512 cube compared to the past 128 cube. The number of points is about 50,000, but with some cubic integration scheme, we can go up to 200,000, and so we can resolve a wider range of scales. So going very quickly through results, we started by investigating the shrinking ring in quiescent normal fluid. And so we have initially a normal fluid, which is quiescent. We have a 256 cube for the normal fluid, only 400 points for the vortices, and the equivalent radius is 7.6 times 10 to minus 3 centimeters. And we investigated 3 different temperatures, so where we have a wide range of variation of the normal fluid density to superfluid density. And the first thing that we investigated was if we could recover the triple vortex ring observed at the early 2000 by Kivotides, Carlo, and collaborators. And in fact, the answer is yes. Here in green, you see the superfluid vortex ring, and you see that there are 2 normal fluid rings preceding and following the superfluid vortex. And here you can see what you can see here are the streamlines, and then we can also see that we see some evidence of a wake, which has been suggested to be responsible for some experimental results. So here we see the shrinking of the vortex ring as a function of temperature, and it is what expected. So we see that as soon as the temperature is increased, we see that the lifetime decreases. When we can compare this with the old, let's say, vortex filament method, where the normal fluid is imposed to 0, and we see that we have the same qualitative behavior. Of course, we will need an experiment with a single vortex ring to determine which model is right, but we know that this is not very useful, but I will come back to this experimental possibility to validate our code experimentally. Interestingly, if we use our model, so where the normal fluid, the mutual friction force is modeled with the low-Reynolds number classical fluid dynamic approach, and we switch off the coupling, we get those dashed lines, which show that actually the pattern is reversed, so that the lower is the temperature, so the higher is the temperature, the higher is the lifetime. So this means it's quite promising, because it means that it is precisely the coupling of the two fluids, which then which then allows to recover the expected results. So then it is possible in our case to show, for example, what is the evolution of the pattern which develops in the normal fluid. So, for example, this is the normal fluid ring, this is the entropy, and we will now look at the evolution of this normal fluid structures, so which in on a slice which is orthogonal to the slice containing the plane. So I wonder if you can see this. So and this is actually what happens. So you see that there is a normal fluid ring develops both in front and behind, and you see this is the magnitude of the squared vorticity, and so it is possible to also to do some measurements. So for example, to measure the sizes and the circulation of the normal fluid around this vorticity structure. And what we get is that the size of this dipole is about some 5 or 6 microns, of course depending on the temperature. And also, if we calculate the circulation around this normal fluid vorticity structure, we get normal fluid circulation, which is roughly half of the quantum of circulation. So then, the last few slides I want to show is that it is an attempt to model some experiments performed by Borner collaborators in the early 80s. Here they had nodes that they created a vortex ring, which was quite likely to be composed of both a toroidal vortex superfluid vortex ring bundle embedded in a normal fluid vortex ring, as they are created simultaneously. And they observed that these structures were actually long-lived. They travel a distance which is of the order of 20 radius of the initial structure. So the question is rather if this coupling is responsible for this long time. And we actually performed some simulations, which I'm going to show here. So here we have at the beginning we have this toroidal vortex bundle, which in this case is constituted by 137 rings, and it is surrounded by a normal fluid ring with where the vortice has a Gaussian profile. And as you see that as time goes by, there is interaction. There is like also small leapfrogging going on, collective leapfrogging, and then the structure doesn't disappear. It stays. It doesn't diffuse too much. It stays, and so the radius, if you see, the radius is similar to the initial radius, and of course there is some diffusion, but it remains localized. Of course, here there is interaction with the wake, but this is of course due to the periodicity of the box. This was only the normal fluid, the superfluid vortex bundle, but and you can see it. And you can see it from the. And here you see both. In yellow you see the superfluid vortex bundles, and in blue you see the normal fluid entropy. So you can see that both from the front view and from the side view, the vortex ring, normal fluid and superfluid vortex ring remain quite localized, and this explains, in our opinion, why Borner observed some long-lived vortices. And this is the dynamics seen from side view for both with both components. So in yellow again you see the superfluid vortex angle, and in blue you see the normal fluid entropy. And so you can see that the vorticity, both superfluid and normal fluid, is stays localized. So with this, I have to find the presentation again. No, it's not this one. Okay. So with this, I conclude this presentation, and I want to conclude by saying that this new method is very promising, and it is likely to be very important to understand, for example, some recent experiments with particle tracking velocimetry. For example, when I talk about this, I think about the wake, which is meant to be responsible for the observed statistic of the normal fluid, and also because it is really the first numerical simulation where the normal fluid can be achieved, where some turbulence can be reliably simulated in the normal fluid. As for example, now we can go to 512 cube for the normal fluid, but with some, we are already thinking about some improvement to go even further. And just to mention, I mean, when you talk with, for example, people doing classical turbulence and you present a 256 cube calculation, they even question if it's really turbulent in the normal fluid itself. Thank you very much for your attention.
Thanks very much, Luca, for a very interesting talk. Of course, I'm
switch on the light, excuse me, because otherwise
I have to confess a slight bias in my view. Does anyone have any questions? Just unmute yourself and ask. Andre has a question.
Yes. Well, thanks, Luca, for a very good talk. Lots of things reminded. Well, first, of course, when you were introducing the Holbein Bakarevich Khalatnikov model, I just was going to tell you that Isaac Khalatnikov has died about 2 weeks ago, aged 101, in Chelengalovka near Moscow. He died on the 9th of January. Yeah. So that's just to put things into context. Right. I have just two very simple questions. When you're plotting the radius of the ring as function of time, it just as a suggestion, it might be good to plot also the square of the radius as function of time, because very simple models of the dynamics of the ring, say in the stationary normal fluid, do prescribe precisely the linear decrease of the square of the radius. So just to see by how much this model will find deviations. And basically then the related development, as some normal components vorticity gets developed around the backbone of the quantized vortex line with some dissipation. Maybe one can just try to build some sort of synthetic approach by renormalizing the properties of quantized lines by adding them a bit of the normal component vorticity and a little bit of damping through the normal component. I mean, just probably I'm just suggesting maybe there is some range of parameters where you can just again treat everything as a single component vortex tangle with a little bit of effective viscosity and renormalization of vorticity or density, and that's basically it. And finally, I just was asking, so is there any differences from the that approach that Kivotidis and others were introducing? Maybe I missed something.
Okay, yeah.
Thank you.
Thanks very much. So actually, yes, you're correct. I plotted the R versus T. Actually, the lines that I showed with which were computed with the vortex filament method agree very well with the analytical derivation that goes R square goes with T, considering the log constant. So this is as a matter just to mention. Considering, excuse me, sorry, what was the third question? I apologize.
I just asked where the
the differences. Yes.
Yes. Okay.
So the differences are first there is the mutual friction force is as an alternative derivation which does not depend on this discretization size on the vortices, which is quite unphysical. Then the numerical scheme is completely different in the sense that we can achieve much wider range of scales, both in the normal fluid and in the superfluid, which it is fundamental to investigate turbulence in both fluids, but also something which probably in past has not been paid with very much attention, is the fact that we have a scheme for forcing the normal fluid, which is a scheme which is normally used in normal fluid in classical turbulence, while actually, for example, in all previous schemes, there was like some linear forcing, which actually didn't allow to reach a statistical steady state, which is what you need if you want to, for example, do some statistics or comparisons between the normal fluid and the superfluid. These are the, I would say, the major differences.
Thank you.
Anyone else?
I could ask a stupid question if I may. You have this this structure or combination of one quantum vortex or one vortex in the superfluid component and then two in the normal component. Perhaps this is something very well known, but can you give some hand-waving reason as to why this kind of structure exists or appears?
Yes. So okay, this is known since the first couple of simulations which were performed in the early 2000s. So actually, you can imagine it can be explained like this. So you have if you have a vortex, which imagine a straight vortex which moves, then this creates two dipoles in the two normal free dipoles around the vortex. If you take a vortex ring which is shrinking, then these two dipoles are tilted, and so when you imagine to do like a revolution of the structure, you get the two vortex rings are actually just as I say, the two dipoles which are revolved around the initial superfluid vortex.
Yeah. Okay, I see.
Anybody else?
Can I ask a question? Do you see some collective effect in the case of the bundle and some kind of reduction? Well, I mean, you see some reduction in the time of shrinking of the bundle, but can you quantify that for example, versus the number of vortices that you have, or?
Yes. So if you use if you have a single vortex, or if you imagine to have a bundle with a very high number of vortices, so you imagine a vortex ring with n quanta, then you take quiescent normal fluid, so you impose to Vn to 0, you've got the shrinking of a vortex ring with some n circulation. What we have observed actually, and that what actually I haven't showed, I can try to retrieve, is the fact that if you, for example, if you simulate the evolution of the vortex bundle with a normal fluid, with stationary normal fluid imposed, you've got a very quick decay of the length. Then you can do something else. You can take the coupled model, but you can start with the initial Vn equals 0, and then let the simulation start, and then you see that actually after a certain amount of time, the normal fluid rotates exactly with the velocity it should rotate, and therefore the decay of the length stops. Then the third simulation, which is the one which I have showed in the presentation, if you start with a normal fluid, a superfluid vortex bundle embedded in a normal fluid which has the same total circulation, then the length stays constant. So actually, you see, going back to your question, you see that with if you can calculate analytically the decay of a vortex ring with the imposed normal fluid, even with n quanta, which is the number of vortices, and you see that it will decay in more or less the expected time, which is because actually the friction doesn't allow any leapfrogging. Okay, but then when you start decoupling, actually this decay is either doesn't occur if you start with a normal fluid ring, or it is stopped once the superfluid vortex bundle has excited the normal fluid so as to stop the decay. This is like a collective effect on the, if you want, on a higher degree. Normally when you have cyclists that drafting, no, you have in front the ones that are behind, like they exploit the fact that the one in front they have the friction, then they move in front of it, and then this means that with the same effort you go you travel a longer distance. In this case, it is even more if you want, it is even more complicated and in a certain sense interesting, because in this case you have that the vortices talk to each other because of the Biot-Savart law. And so in this case you have that this collective talking between the vortices, it is necessary to the rotation of the bundles. It is necessary to excite the normal fluid, so to minimize the friction.
Okay.
Time for one quick question. If not, please thank me in thanking Luca for kicking this series off. I'll pop in the chat the link to the website that we've set up for this webinar series. The email addresses of the organizers are all on there. There are people who here who aren't on the mailing list, which is great. We set this up with a UK-based mailing list just because of a funded special interest group that we had, but hoped that more people could join through word of mouth. I will try and download the participant list from this meeting and automatically add people to it, but just in case I bugger that up, please just email one of the organizers, and you know, we can add you to it and be notified about future meetings. In 2 weeks, Davide will be giving the webinar, and I'll email out details close to the time. So I think that's everything. So thanks everyone for coming, and see you all in a couple of weeks.
Well, thank you very much.
Thank you, Luca.
Thank you.
Thank you.
Thanks, Luca. Thanks, Andrew.
Thanks, Luca.
Thank you, Luca.